So, anyway. Okay, so this is our Wright-Fisher model. So we think of an urn in generation n. So generation n, so our time is discrete. In generation n, we have capital A and little a alleles. So a bunch of them. So there are 2n of them, right? So there's 2n. So think of that as 2n balls in an urn with labels and labels, right? So then our idea is that we're going to get balls to populate another urn, okay, in generation n plus 1. So the basic assumptions here are constant population size. So there will be always 2n haploid individuals at every generation. The other assumption is non-overlapping generations. So at every generation, every individual dies after they reproduce and populate the next generation. So it's like a new set of children every generation. And yeah, so you have deaths and rebirths every generation, and then you have random mating. Or it's generally pan-mixture. There's no population structure or anything, right? And so this essentially corresponds to sampling from here with replacement. Okay, this is exactly the basic model. So so you sample from here, one at random, and throw it here, basically make a copy, and then you again go back here. There's still 2n guys. Sample one at random, throw it back there. So you repeat it 2n times, and then you get your new population. So that's basically Wright-Fisher model for a 2-allelic system. So now, let's set up a Markov chain. So this was the reason why we did Markov chains in the last 04 foundations course. So the idea is that at generation n, I individuals, balls, have allele A. Right, so we're just encoding the number of capital A alleles, and so 2n minus I individuals. Have small a. And then 2n will always be the number of haploid alleles. In a diploid population of size n at this biallelic locus. Okay, so we're sort of studying the system exactly at one locus, one position, and that is biallelic, so only 2 forms, so it's very simple. And also, this little locus we're studying does not recombine. Okay? It could be part of the Y chromosome, or it could be part of mitochondria, or it could be just one nucleotide. So it's the simplest possible setting. So then to build up the n+1 generation, we choose from the urn at generation n. 2n times with replacement. So this gives us this entity, so x, the random variable x at time n, x of n, is going to be the number of A's, number of capital A alleles in generation n. Time is discrete here. And so it's not hard to see that xn as n, let's say we start observing it from some time 0 and we move forward, marching. This is a Markov chain. What is the state space of this Markov chain?
So the next generation depends on the previous one, right?
Yes, I mean, yeah, so it's a Markov chain because the next generation only depends on the current generation, not the past. But the Markov chain has a state space, right? It hops around somewhere.
From 0 to 1?
Yeah, so 0 to 2n. It's because this xn is keeping track of the number of capital A's, right? In any given generation. So the number of capital A's can be 0, because there could be no capital A's. Everything is little a. Or it could be just 1, or all the way up to 2n, right? So that's our state space. It's like the lily pads now, or frog process, or whatever, frog jumping. So now why? Well, of course, it's a Markov chain because the probability of xn plus 1 taking the value j, given xn, say taking the value I, and xn minus 1 taking the value, say, lowercase xn minus 1, and so on, all the way up to when we started observing the system, took the value little x0. This whole history, so the probability, this conditional probability of what will happen the next time step, given the entire history, only depends on the current state. Equals j, given xn equals I. So that's the Markov property, because we're just sampling from the urn that's currently there. And we define this. We define this to be lowercase pij for convenience. So this will be our entries of our transition probability matrix, right? Because that's what we need to define the Markov chain. So okay, so now what is that exactly? The lowercase pij. So how do we get to j capital A alleles when the urn at time n has only I capital A alleles? I told you the sampling machinery, right? So what is the probability?
So it's the frequency?
Yeah, so the frequency of the capital A alleles will play a role. But I want to know, what is the probability that the next generation, the urn, will have exactly J capital A alleles, given that it has I capital A alleles now.
Something like I over 2n and then to the power j.
Yeah.
You need to be successful at j times 1.
Yeah, very good. So let's start. So what's your name again? Huh?
Rebecca?
Oh, Rebecca, right, sorry. Okay, so Rebecca's plan is like this. So she says there will be, and also Dimitri said the same thing in some sense. So I over 2n is the frequency of capital A alleles, and she wants to raise this to the power of j, right? Because this has to happen j times, so you have to make j choices where you pick capital A, right? And then there's 2n minus I, which is the number of little a alleles. So you have to choose that 2n minus j times, right? You're okay with this? And if you think about it, what is this? I'm basically, I can think of this as the probability of coming up heads in my Bernoulli. This is the probability of coming tails, picking capital A and little a like heads and tails. And you see, this is P and 1 minus P, right? Because if you add these two, it's 1. So these are Bernoulli probabilities, and then I'm simply saying, what is the chance I get j heads and 2n minus j tails? It's exactly what you've seen before. But what we need is a little more than this. Yeah, so for example, this doesn't say the order in which I did my j's and. So for example, let's say j is 3 and 2n is just 6, okay? So then I could have had picked capital A, capital A, capital A, little a, little a, little a. This is 1. And let's say my j, I want my j to be 3, my 2n is 6, right? So this is one way. And that has probability this, right? It will be whatever. Let's say I is something. I is 2, let's say. So we can, but also this one, right? If I had 1, 0, 1, 0, 1, 0, I still have 3 A's I picked in the end. There will still be 3 A's, but then the order is different, right? So I have to account for the order in which I'm picking, and I have to find out how many distinct orderings are there. This is something we haven't covered in the foundations, but sort of been waiting for this moment. So to do this, what you have to do is, first of all, find out what is the total possible orderings, right? So, so basically, if I looked at all possible orderings of 2n elements, right? So my initial choice is 2n. I can choose any one of them. Just label them 1 through 2n, put labels on them. So then the next one I can do is, next choice is 2n minus 1, right? Because I've chosen one already to place first. Then I have 2n minus 1 choices, so I can choose one of those. So basically I can keep multiplying like this. So this is 2n factorial. Right, we saw this in permutation. So that's the total number of ways I can order 2n elements in a row, right? So okay, that's all possible orderings, but of those possible orderings, I don't want everything, right? I want to divide this by so for each ordering, I don't care how the j's are ordered within it, right? So if I divide this by j factorial and 2n minus j factorial. Okay. So this is just j times j minus 1, and it's all the way to 2 times 1, and multiplied by 2n minus j factorial. Okay. So this essentially, only gives me the total number of 2n factorial orderings where there's exactly j1s and 2n minus j0s. Okay, this is called the binomial coefficient. So this is basically 2n choose j. So the notation for this is like this. Okay. And so what I have to do is put 2n choose j here, because this gives me all the orderings that will give me. So what we've written here is actually the probability mass function of a binomial random variable. And the binomial random variable has two parameters, okay? So, so you normally think of the binomial random variable as having a parameter for the number of trials. So here it's 2n, or 2n independent trials, okay? And these 2n independent trials have a success probability. So Bernoulli success probability, in this case it's I over 2n. Okay? And the way you actually construct the binomial random variable is simply by summing Bernoulli random variables, which you know already. In fact, that's what we Bernoulli random variables with success probability I over 2n and n of them, 2n of them. And so let's see. Yeah, so j k from 1 through 2n. So you have 2n independent Bernoulli random variables with success probability I over 2n. You simply add them, and that independent addition of Bernoullis is the definition of binomial. Okay? And this binomial coefficient accounts for the number of ways you can embed j1s in a sea of 2n zeros and 1s. Okay? All right.
So you just sum 2n Bernoulli.
Independent, yeah, Bernoullis with probability I over 2n. So this is
K, the index k has nothing to do with it.
Yeah, I use k because I don't want it to get confused with this I, right? Because this I is from the earn, right? That's the number of capital A's. That's fixed. But I'm just putting some arbitrary.
Just Bernoulli sub k, so that they are different. The Bernoulli.
It's not the same Bernoulli variable for each.
No, it's the same.
No, you can have a random variable xk, and each random variable is Bernoulli distributed.
Oh.
So then you have the index.
Yeah, okay, that's a good way to think. Well, yeah, so you're asking what's k. Well, I just want this sum k times. It's the same. Right, I mean, I'm basically saying this is just Bernoulli I plus n plus Bernoulli I over 2n. 2n times 2n sums, you know? 2n entries in the summation. So, okay? So let's continue. So what is the mean, the population mean of the binomial random variable? Can you guys guess? Okay. P? Yeah, time 2n times p sounds good, right? Because, yeah, so the expectation of this guy, let's say this is x. What do we actually call this? Is x of n or something? is going to be 2 capital N times I over 2n, right? 2n's cancel, so it's just I for the same. So in general, it's n times p, the product of the 2 parameters. Okay. Okay. So next, what we're interested in is in the long-term behavior of this Markov chain. So this guy starts at 0 when we start observing, and then it keeps going. This Markov chain, the Wright-Fisher Markov chain for the number of A alleles among 2 N alleles. So, what do you guys think? What will happen to this Markov chain?
Either converts to 0 to 1.
So he says it will converge to either 0 or to 2n. You guys agree? Yes. Yeah, so 0 and 2n are absorbing states, right? Because 0 means there is no capital A alleles, so it's all little a in the urn. And if it's all little a in the urn, you're going to always be stuck there. Every time you do 2n samplings, right, you'll always get little a's. So the population gets fixed with the 1 allele. Or if you have all capital A's, and then you're stuck there, because then every time you do. So yeah, so either xn, as n goes to infinity, goes to 0 with no A alleles. Right, that means all little a's. Or it goes to 2n with no little a alleles. All capital A alleles, right? So this is because 0 and 2n are absorbing states for this Markov chain. So, and this just means the chain can never leave 0 or 2n once it is there. So it's like, yeah. Oh, sorry, someone blessed someone. So we say fixation has occurred when xn enters an absorbing state, right? So this is again just some genetic lingo, because the whole population is fixed at this allele, at this locus, at the same allele, right? So there's no variation, and it's reached a sort of fixed point. So fixation time, tau, is again another quantity of interest. How long does it take to reach fixation? Right? So in other words, this is the first time the population is all A's or all capital A's. Okay. So formally, you define tau to be the minimum of the set of all n such that xn is 0 or xn is 2n. Okay. So that brings us to our theorem 1.
So this model is like a simplification for explaining entrance evolution?
Yeah, so the plan is, I think I have 6 theorems, I don't remember, yeah. So I'm trying to give you a formal construction of what's called the Kingman coalescent. So Rebecca, you studied Kingman coalescent in the course, right? Or whatever, you said you took a course on coalescent theory?
I'm checking.
Yeah, yeah.
No, we just did the Wright-Fisher.
Okay, so you didn't look at the genealogical process of the sample back in time?
No.
Okay, so that's good. So you'll learn something then. So theorem 1, in the Wright-Fisher model, the probability of fixation in the all A's state, given you start with I capital A alleles, okay, at time 0 is this. So the probability of x tau equaling 2n, so everyone being capital A, given you initially at time 0 start with I alleles, is simply I over 2n. Okay. It's very simple, it's called a theorem for historical reasons. So the proof is not that complicated. So since 2n is finite, right? It's not infinity, it's a finite number, fixation will happen. With all capital A's or little a's.